All right. Welcome everyone again to the RL course. Today I'm going to talk about meta reinforcement learning. I actually don't know, Chris, where the typo has happened. Is it in the course?
In my announcement email today.
Okay, good. Great. So I know that. I would like to start first with some of the slides that I couldn't present in our previous lecture. Some of those slides are actually needed to understand the few concepts that I'm going to introduce in this lecture. But since we probably will have not enough time, I have to go through some of them pretty fast. As you may remember, we talked about using generative models to basically learn action distributions. And the main motivation for such a design choice was that we would like to limit the distribution shift between the action that a policy is taking and the action that are in the data buffer. I'm also gonna talk a little bit more about how we can use generative models together with reinforcement learning, but I would like to extend the previous formulation to not only model the next action, but a sequence of action starting from current time step. So let me just try to formulate this problem a bit more mathematically. Let's assume that we have a robot here, and a robot is supposed to shoot the puck, which is here, to a target position. This problem setting basically requires the robot to perform a sequence of actions, starting probably from the top and then going all the way to be able to shoot the puck with the hockey stick. And then once the actions are done and the puck is in the final location, we can give the final reward to the robot, which can be like, if it successfully could shoot the puck into the right position, it would receive a +1, let's say, reward. Otherwise, it won't receive any reward. So this is like the setting that I'm going to talk about. This setting is called terminal reward, because the reward is only received at the end of the episode once everything is completed. And so definitely it's a very sparse reward setting. And another important thing about this setting is that you can basically learn a feed-forward controller, basically that the condition on the current observation, it can generate a sequence of full actions. This is a little bit different from what we discussed previously. So previously, most of the time that I was talking about the policy, I meant really a feedback policy. But here, I'm gonna, for a few slides, I'm gonna only talk about feed-forward policy. Okay, now let's see how we can train a feed-forward policy. Right now, by the way, the disclaimer is that I'm going to talk a little bit more about robotics, but hopefully some of these ideas are still possible. I got a message that the slide is not in the shared presentation. Is it the problem?
Yes, I think that's in your presentation from last week.
Yeah, it is. I mean, of course, it is.
Because you shared a new slide for today.
No, it's, please have a look at my previous, because I mean, I couldn't present these slides for the previous session. So that's why I'm presenting some of those slides first, and then I go to the meta reinforcement learning topic.
Okay. Thank you.
All right. So the problem that we're trying to solve here is that conditional initial observation, we would like to find a policy that generates a sequence of actions. So tau here refers to a trajectory of actions that the agent is taking for a number of time steps. And then once the policy outputs such a trajectory, we implement it on the robot, execute the action on the robot, and then finally we receive the terminal reward at the end. So then this problem can be formulated as maximizing the log likelihood of reward condition on the current observation, and the parameters. I mean, this capital theta denotes all the parameters that exist in this policy. And okay, one way is to actually marginalize over all possible trajectories and do the optimization from there. But it's going to be a bit difficult to marginalize over trajectories because they can be super high dimensional. So in this robotic example, they can be easily about 500 dimension. So it's not a good idea to actually marginalize over possible trajectories over the trajectory space. So instead, we can still use the same idea as I introduced in the previous slides of using generative models. So here, a generative model condition on a latent variable will generate a trajectory. And basically, then the question, again, like as I introduced in the previous lecture, the question is that how to train a sub-policy. I guess I called it sub-policy in the previous lecture as well. But the question is that how to find a sub-policy that condition on the state find the distribution over the latent variable, which when given to the generative model can generate the full trajectory for us. This is a nice thing because now to find the log likelihood of the reward, we don't need to marginalize over all possible trajectories, but we can marginalize over a latent variable. Here I denoted this as alpha. Alpha can be very low dimensional. It can be like 2-3 dimension. Most of my research, I never use more than 6 dimension for alpha, but I would say 2 and 3 are also okay. Depend, of course, on the problem setting that you're trying to solve. But then this is like a possible way for you to still learn a complicated policy and implement it on a robot safely. The good thing about this formulation is that first of all, the generative model can use your offline data. Then when you're training the entire policy, you don't start from scratch. That's one benefit of this formulation. But the problem here is that the offline data should have high quality. You can't just expect some random data to be used here. And then this is safe to run on the robot. Of course, you have to make sure that you're not providing inputs to the generative model that are outside the training range. I guess I talked about it in our previous meeting as well. But if you try to put some limits here, then you can train a sub-policy, and the sub-policy basically, once it's trained, it's able to regulate the generative model to produce the right outcome. This problem setting is also, you can also train with this solution even if you have sparse rewards, because now you're actually solving a multi-arm bandit problem. You're not solving a sequential decision-making problem anymore. You actually have one state, one action, which is now your latent action, and then one reward at the end. So it's a multi-arm bandit. Basically, it's better to call it contextual multi-arm bandit. And it's no longer a sequential decision-making problem. So you don't have a problem with credit assignment. You don't have a problem with safety of running stuff on robots, because the good thing here, as I said, the trajectory that are implemented on the robot comes from the generative model, and that makes it possible to run them safely on the robot. I have some more slides to talk about, but I have to skip them because otherwise it's going to take quite a lot of time. But very shortly, I have talked about how we can train the generative model. We can use, let's say, VAE models. We can use GAN models. So there's not, I mean, any kind of latent variable generative model should be able to do the job properly. Based on my previous research, we showed that VAEs are slightly better for this problem setting, but okay, this part can be trained unsupervised. This guy here can be trained with regular reinforcement learning algorithm, like policy search. I have used previously PPO, proximal policy optimization, to train this guy. And it's also possible to do some sort of end-to-end training in a supervised setting. these are the slide that I have to skip, but I can actually go to the very last slide. Okay, this is about an expectation maximization formulation that you can use in order to convert the policy optimization problem into this. Oh, sorry. Into an EM policy training, in which in the E step, we are, okay, here you can assume that Q denotes the policy in the before the update. So if we are gonna update the policy iteratively. So you can assume that Q here denotes the policy before update. So in this case, in the expectation step, you're gonna update the policy to stay close to the policy. I mean, sorry, this is the policy that's going to be updated, and this is the old policy. I'm saying it wrong. Sorry again. This is the old policy, and Q is the policy which is going to be updated as the next time step. So I made a mistake here. And so this term forces the updated policy to stay close to the previous policy. This kind of formulation has been called in the literature as trust region policy optimization. And basically, the main idea is that whenever you're updating your policy, you should not deviate too much from the previous policy. And this is a reward-seeking term, which says that the new policy should actually optimize the reward. And then we have a maximization step in which you train the policy supervisedly by minimizing a KL divergence. Here, if you're assuming that the two policies are the same and then this Q is just a new policy, you can simply copy the parameters of the new policy to the previous policy pi theta prime. So you don't need to actually minimize a KL divergence term. But the good thing about this formulation is that it does, if the two policies are not the same, let's say one of them inputs images and the other one inputs states, you can still use the same formulation. And in this case, you have to minimize the KL divergence as the formulation says. But anyway, my main point here is that if I go back to this slide, the main point here is that you don't need to basically, if you use a generative model, you can split this big policy into two parts. The generative model will be trained unsupervisedly, and this sub policy can be trained using, let's say, a regular reinforcement learning algorithm like PPO. And if you want, you can also use the formulation that I mentioned as expectation maximization in order to train the entire thing end to end, conditioned on the fact that your sub policy can be like different. You may have two different sub policies and you would like to train them together. But anyway, unfortunately, I can't go into more details about this. Some experimental results. This is for hockey shooting. As you can see, the red denotes the target position, and the robot has to find a full trajectory basically to shoot the puck. Here is another example for basically throwing ball into basket, different location. And here is basically same task, but this time I guess the robot learns to do it by bouncing the ball. And we use exactly the same kind of formulation for training these policies using generative model, first training generative model to basically learn a generative model based on offline data set that is provided to the agent. And here's just some more real robotic experiments. The task is to shoot to this guy. And then we train a sub policy to regulate the generative model to basically complete the task considering the target object. So here the target is this Pikachu, and for the others are the target are given by the red dot or the basket position. All right, now I'm done with my lecture about offline reinforcement learning. Now I can move on and talk about meta reinforcement learning. Is there any question before I start the new topic?
Yeah, Ali, may I ask a question about the evaluation methods?
Sure, please go ahead.
So here you introduce many like RL with generative models. Then how do you compare different models? Or let's say, how can we say which one is better than another one?
By the models, are you talking about generative models?
Yeah, just something in general. So you have different methods. How do we compare methods here, like RL with different generative models? How can we claim one is better than another one?
And by one better than another one, you mean one generative model better than the other generative model, or you're talking about this framework compared
Yeah,
to?
this let's say it's just something in general, how to compare different RL algorithms. Because
Okay, I see. So generally, when you want to compare something, you have to look into two things. One is that how fast the agent can learn something, and how good, and second, how good it learns the thing. So in reinforcement learning, if you don't do it in simulation, most of the time you're very, very keen on data efficiency aspect of the reinforcement learning. So you would like to learn the policy provided as little as possible samples or data from the real hardware. So this is like one of the main consideration. So whenever you're comparing two reinforcement learning algorithm, you look at the performance, learning curves, and see which one can converge faster. That's one aspect of it. And the second thing is that, okay, how good the policy, the train policy look like. And for that, you typically look at the return that you get from the policy. So if you plot policy training versus return, you would see that which one gives higher return. There are also other aspects that can be important. One is like safety. Sometimes you would like that, okay, it's okay if the policy training goes slower, but I would like to make it safe. I guess Chris is going to talk about it in his lectures. Another aspect can be like you may have some limitation. Let's say the agent should not have like abrupt changes in behavior, should not have, how to say, sudden drop in performance. Things like that can also be considered sometimes as merits when you're training a policy using reinforcement learning.
I see. Oh, thank you so much. And another following up question is that regarding like the return and the rewards, is there any guarantee that RL can learn the optimal policy in the sense of return and reward?
There are guarantees, but these guarantees are typically, it's possible to just show that, prove that things will converge to optimal solution if you basically work in discrete time step. And yeah, and assume that you can provide sufficient data to the agent. For discrete state and action spaces, they're proof for these algorithms to work. But the method that I'm talking about here generally, it's harder to have any proof for them because most of the time I'm talking about continuous state space and action spaces. And that's one difficulty. It's quite high dimensional. I'm using neural network to approximate. It's based on lots of estimation approximation. So in general, whenever you look into my lecture, most of the time I don't have any guarantee or proof or thing.
I see. Thank you so much. That's pretty clear now.
Okay, thank you for the question. There's another question.
Yes. First of all, did you book 2 hours this time, or are we still at 1.5 hours?
It's okay for me. I can continue up to 3, but I don't know what. Chris, you're the boss here.
But the second question, the real question was, you said that you trained the generative model in an unsupervised offline manner. What is it? What is the training objective then? Is it?
Do you remember about variational autoencoder object?
Okay. So it's the same.
Exactly.
Yes. Okay.
Sorry, this lecture should have been like presented right.
Yeah, I guess. But yes, thank you for reminding me.
No worries. Thanks for the question. Okay, great. If there's no more question, then I can start with meta reinforcement learning topic. Okay, let's start our new topic, the main topic for this session. Okay, what is the problem? What basically meta RL is trying to do for us? Why do we need meta reinforcement learning? So first of all, if you look at reinforcement learning, here I have just mentioned a few drawbacks of policy training or learning control algorithm using reinforcement learning. The first one is basically this algorithm most of the time train a policy from scratch, which means that you start from a random policy and then you keep training them until you get a good performance. Reinforcement learning is based on trial and error, and the main idea is that you do something randomly. If it turned out to be good, you try to reinforce the action in that context. So this approach then is unfortunately very data inefficient. It requires a lot of data to be able to produce something good by chance and to reinforce it and to make it more to happen more often in future. So that's also another problem with reinforcement learning. And another issue is that once you train a policy, unfortunately, again, it doesn't transfer well to new condition or new domain. Here's an example. Let's say that you have trained a policy to shoot a hockey puck on this robot in simulation. Then, if you use the train policy in simulation and implement it on the real robot, that's not going to work, unfortunately. Even though the robot appearance is exactly the same from simulation to the real robot, and you are trying to do your best to match the dynamics of the task from simulation to the real world, but still there's some basically discrepancies between the simulation and the real world. And because of these discrepancies, the learned policy simulation, unfortunately, does not work on the real robot. Another problem is that basically, if you look at here again, if I change the robotic platform from this platform to another, again, we have problem because then this new platform would look like out of distribution. So even our setting is the same. So the dynamics of the puck, how they move, and the hockey stick, everything else is the same, but just the robot is different. Still, you can't reuse the policy which has been trained here on this new robot, and you have to start from scratch. And finally, whenever you train something for one task, even though there is some common structure between these two tasks, still you can't basically benefit from it. And whatever you learn here, you can't reuse even part of it when you want to learn a new task, even though there are some similarities between these two tasks. The main idea that I'm going to talk about in meta reinforcement learning is how we can leverage prior knowledge, the knowledge that we gained from learning other similar tasks to speed up policy training whenever we are given a new task. So this is the main topic that I'm going to talk about for today's lecture. Meta reinforcement learning can be applied basically to any problem domain, as long as it's reinforcement learning, and you can define some tasks that have some common structure. But most of the lecture, I'm going to talk about robotic setting, but I think the ideas that I'm introducing here, most of them are general enough to be applied to other problem domains as well. Do we have any question here?
Yeah, just a quick clarification question here.
Sure.
So here, so what is the difference between the meta learning part and transfer learning or domain adaptation? So here, I feel they are quite similar.
What was the first one? You said meta reinforcement learning and the transfer learning part.
Transfer learning and domain adaptation. Yeah.
Okay, basically, I'm gonna talk a little bit about different ideas from transfer learning. So there are similarities between these different approaches that you mentioned. One important difference about meta learning is that the basic idea here is that you don't train a model, but you're training a learner. So that is, I guess, the big difference between transfer learning and meta learning. In transfer learning, you learn a model here, for example, and then you transfer the learned model to a new setting. This is basically transfer learning. In meta learning, you don't learn a model, but you learn a learner. You learn some agent that can train other models. And if that agent is general enough, then you can expect it, if it can learn, if it can basically help the agent to learn this task, it should also be able to help the other agent to learn the other task. So this is basically the big picture of meta learning. That's why it's also called learning to learn. But this is my personal opinion. We're not there yet. Most of the algorithm that I'm going to talk about, of course, there are some, you would see still this concept of learning to learn. But I would say that sometimes maybe it's not very convincing that, or very clear what are the real differences between transfer learning and meta learning. But anyway, let's, I mean, please ask me this question again when I'm talking about a different approach. Maybe it would be more clear to talk about this question in those slides.
Yeah, thanks. Yeah.
Do we have any other question? All right, let's move on. Okay, on the left, you see standard machine learning pipeline. So generally, you're assuming that you have a data set, you have a huge neural network, and you define a good loss function like cross-entropy loss. You have access to some GPUs, and then you would let stochastic gradient descent to do the magic for you and to train your neural network that would basically do the job for you. So here, for example, if the task is to classify different cars, then you would provide an input to the network. It will be processed with different layers, and then it will give you the output. In future learning, our problem setting is slightly different. In future learning, we typically assume that we don't have access to a huge data set. We're typically assuming that we have access to just few data points. Here, this is like one basically training data set for our future learning case, which consists of 5 training examples. So I guess that's not very difficult for you as human to, whenever I'm just giving you, I mean, if you look at this, you would immediately say that, okay, now this is a novel test input. I want to do the classification. So I guess it's not a big problem for any of us to say that, okay, this belongs to this class and this belongs to this class. So this should be fairly easy and straightforward for us as humans to decide that to do the classification. But for machines, it's extremely hard because having access to 5 classes is not really sufficient to understand the concept. I mean, because most of the time they start from scratch. And this number of data is really not sufficient for them to understand the basic features or basic features that makes this class different than the others. So, and by the way, some of the contents that I'm talking about is borrowed from the meta-learning course done by Professor Chelsea Finn. I have put a link to the course at the end of my presentation. So if you are interested about learning more about meta-learning and also meta-reinforcement learning, I really encourage you to look at that course. Both the lecture slides and also YouTube presentation are available publicly. So you can have a look at them as if you're curious to learn more about this concept. Okay, so the key to solve future learning problem is basically to learn a structure between different tasks. So we as human are good because we have a very strong prior knowledge about how different things would look like in reality. So, and we use our prior knowledge to be able to do this classification task without any effort. But for machines, basically, we don't have such a possibility unless we train we can train on a lot of different tasks, and we can learn common structure and understand how tasks are related to each other, and basically reuse this information whenever we are provided such a future learning task at the test time. Do we have any other question so far? Okay. I would like to first start with a very simple idea. If we're given this task, one way is to basically learn a classifier using data sets that are available like ImageNet. And basically we can train them, and I denote the parameter theta here as the parameters being trained on the classification task, which is defined on this data set. So this data set basically here can be the ImageNet. And then we can do basically few more gradient updates, but with the loss, which is defined by the new training example. Here I denoted it as DTR. And then we can, by computing the gradient with respect to theta, we can update the model, which is trained on ImageNet, let's say, with some few gradient descent, and obtain a new model, which hopefully would work on this few shot setting. This is, of course, one possible solution, but in many cases, in practice, it doesn't work because, yeah, I mean, the initialization, which is found by ImageNet, most likely is not a good initialization to basically obtain a model for this new task. And if you just naively apply this gradient descent rule here, most likely you would not be able to learn a good model here. We can do it slightly better and basically do the training, formulating the training problem by basically training a model that is actually good at future learning during training. And then whenever a test example is given to us, we can basically use the same model, which is trained in a similar setting to give output for our new examples, new classification example here. So I'm first going to talk about supervised learning setting. Assume that we have two models. One is the meta learner and the other is the task specific model. So here I'm using theta to denote the parameters of the meta learner. but and phi to denote the parameters for a given task. So here, this is a task. And in order to solve this particular task, I need to obtain parameters phi. Yeah, we have a question. Please go ahead.
So the task over here is to learn the learner, right? If I understand it right.
Can you repeat your question again?
What is the task over here? Yeah, over here, we are not learning to classify. Instead, we are just learning to learn or learning to build a function, right?
Basically, the task, I mean, if you look at the final task, is the classification task here. So we are providing 5 different examples saying that this is class number 1, class number 2, 3, 4, and 5. We're providing this training data, even though it's just like 1 sample per class, but still it's the training data. And given this training data, our goal is to learn a classifier, which is G of phi I. I mean, I refers to the fact that we are talking about this particular task because we can define a lot of these tasks. So our task is to learn a classifier G with parameter phi I that would basically work well on novel test objects, which are given here, for example. This is our task. Is it clear now?
Yeah, thank you.
No worries. And basically, we can formulate this problem as a meta-learning. So then we train a meta-learner, F theta, that is trained on a huge amount of similar tasks. So we can basically define a lot of such tasks in our database. You know, this is one task, as I said, a test task, but I can create a lot of those tasks in my training. And then I can ask a meta-learner to output the parameters of the classifier condition on the training data set. And the training data set here, I mean, basically this few samples that, you know, each of them is now a new task. So tasks are denoted by T. I mean, this T, of course, I don't know what should I call it, but let's call it T. So T1 consists of these training example and this test example. I can also call them support example and query example. Support examples are the one which are given to the meta learner to output the parameters, and the query examples are the ones given to the classifier, which has been resulted from the meta learner to compute the loss with respect to the parameters of the meta learner. So these are the query example. So I can basically define a lot of such tasks and then optimize the parameters of the meta learner such that at the test time, it can actually do a good job. And the loss function can be defined like this. So our basically task is to obtain the parameters of the meta learner. And by maximizing the loss or objective, let's call it, on test example, then the few shot training example or support example are given to the meta learner. Is this objective clear? Because I guess that's quite important to understand it before I can continue.
No, I think it's kind of hard to understand the objective function.
All right, let me just try it again. So is it first clear that for each task, I mean, is it first clear that this is one task and this is a second task, and we have, let's say, millions of such tasks in our meta training data set?
Yeah.
Great. So then each task consists of 2 sets of data. One, I call it support data. Support data, the one with green borders, are the data that are given as input to the meta learner. And meta learner generates a classifier. You know, it generates the parameters of a classifier, but we can actually say that it generates a classifier for us because G is known. And if we know the parameters of G, then we have the classifier. So meta learner, conditioned on the support examples, generate parameters for a classifier. And then we can provide our query examples, these with blue borders, I mean, from the same task, to the classifier given by the meta learner to compute the loss. I mean, if we have a classification task, we can compute the cross entropy loss on these example, considering that, okay, this is my classifier, this is my examples, I know the class label for them, I know the input, and therefore I would like to basically compute the cross entropy loss for these data points. And once we have computed our objective, I mean, when we're talking about cross entropy loss, then we have to minimize it. But okay, assume that we have an objective that we are maximizing, then the goal of meta learning is to obtain the parameters of the meta learner such that this objective is maximized over all different tasks in the meta training data set. And how this loss is constructed. So first, have a look at this part. This part means that given support examples, my meta learner for task I should generate some parameters, phi, right? This is this part. It generates the parameters for the classifier for my example. And given the parameters of the classifier, and the data that I call them query data, the blue ones, I can compute the loss for these tasks. And the goal here is that I would like to maximize or minimize my objective for all the mini batch samples that I'm getting from my meta training data set. And once this is trained, once I get the theta parameter, I can simply use the theta parameter on a test example, on the support sample from the test task, and generate the parameters for the classifier, use the parameters for the classifier to classify new task. Is it more clear now?
Yeah.
Okay, great. Happy to hear that. Then let's move on. Yes, please.
A quick question. The tasks T1 and T2, those are human specified, right?
Basically, you can say so, but in general, whenever you have a data set, can you say that the data set is human created? If the answer is yes, the answer for this question is also a yes. But sometimes you can automate basically generating a database.
But I mean, it's like, it's still we decide what that task is. If it's like, oh, decide if this is a cat or not, or it's predicting the next trajectory. That is like the meta. There's not a meta trainer that is setting an objective for the meta learner to perform.
This is kind of true. Still, we don't really create a meta learner that is like task agnostic and can be applied to any domain. We are basically gradually trying to move there. But I agree with you. This is still very engineered problem setting and still require a lot of input from the human designer, how the task should look like. Yeah, I totally.
If I'm working with text data, I have my like toolbox of like, okay, I know these are the things you can do with text data in a unsupervised or self-supervised setting.
Exactly, right. Good. Is there any more question here? All right, now I would like to talk about meta reinforcement learning. So first, let's think about what is how our meta training task should look like. Here's a very, very simple example. I mean, real world examples are much more complicated than this, but let's focus on a very simple case here in which we have a AND agent. And here, simply I can define different tasks as moving into different directions, running into different direction. So here is just, I'm showing like 3 different tasks that I consider for the agent as my meta training task. And here, each task can be a different MDP. Remember, a Markov decision process is characterized by a tuple consisting of a state space, an action space, a probability distribution of state transitions, and also a reward function. If you want an agent to move in different direction, the state action the state action spaces and also the state transition probability remain the same, but the reward function would be different because for this task, you would reward the agent whenever it runs very fast in the left direction, but it would be different for the other tasks. So that's why I'm saying the agent at the meta training is solving different MDPs. And at the test time, basically, the agent is given a new task. It does not know anything about it yet because it hasn't basically received any reward and it doesn't interact with the new task. But the basic idea here is that based on the information it has learned from solving other tasks, now in a very similar way to the supervised learning setting, the agent now has to basically learn super fast from its previous knowledge to learn the new task much faster. And remember that our goal here is to learn common structures between different tasks. So we're assuming that these tasks are sampled from a distribution of tasks. And because of that, and we assume that in that distribution, tasks have some common structure. For this particular example, basically the common structure is because of the fact that there is like same dynamics applied to the agent, same at the state space, same action space, but the difference is, as I said, is only in the reward function. Assuming there is some common structure between the different tasks or different MDPs here, we would like to learn a meta model like F theta that basically receives a bunch of state action transition and rewards, and then map them to the parameters of the policy. If you apply those, if you give these parameters to the policy, then basically this policy should be able to solve the new task at the test time. Again, the objective very similar to supervised learning, but this time we are maximizing a reinforcement learning objective, and our sum is over all the MDPs denoted by M here that exist in our meta training tasks. Do you have any questions so far? Okay, let's move on then. Something that I would like to mention before I move on with meta reinforcement learning. Let's assume this simple task here. It's of course not very simple, but anyway, it's still I would say a toy task. Assume that we have a training data set or support set in blue here. This training data set consists of positive samples and negative samples, or let's say class 0 and class 1. So for positive samples, we have this images, 5 different picture of human faces, and also the same for the negative one. So if you look at the training data, you would realize that for the attributes that are in common for all positive samples are probably these attributes. They all have makeup, they are all young, and they have their mouth open, while these attributes are not there for the negative examples. This is so far so good, but this task is ambiguous because what if I provide an image that has 2 of the attributes, but not the third one? Would I consider them as positive or negative? So the main, the most important thing I want to mention here is that defining a task like this is basically ambiguous. And we may not really understand what the task is if we only are provided few training examples. What meta learning in supervised learning basically do is, okay, it tries to formulate the meta learning solution as a probabilistic model. So it would say, okay, if I'm given a new task, then I would basically deal with it by considering some uncertainty. And then I am not only generating one classifier, but generate a bunch of classifiers that with the hope that, okay, one of them is able to capture the main task. And if you're able to interact with a task like in active learning setting, then you can actually ask for more samples. The agent can ask for more samples to actually understand what the task is. So is having makeup really important for the task, or it's that the fact that being young is more important? So the agent basically can ask for more samples to better understand from the training data, to better understand what the task is. This is about supervised learning. But in reinforcement learning, we actually does not have, I mean, this is basically something that is already there. So with reinforcement learning, we're assuming that we have a active learning, or basically online training. And here, whenever we are giving a new task, the agent basically does not know anything about it yet. It has to interact with the environment to understand first what the task is. So very similar to this example, that the agent may not really figure out what the task is, and it has to ask for more samples. Whenever the agent is situated in an environment, even though the task, we know that it comes from the distribution of meta training task, but still the agent does not know anything about how the task should be solved. That is why in meta reinforcement learning, we typically have two different policies. One is an exploration policy, which, given a new task that I don't have any information about it, it has to explore efficiently in the state and action space, or let's say it has to explore efficiently its environment to first understand what the task is. And as soon as it collects sufficient amount of trajectories or experiences that can uniquely or actually with less uncertainty identify the task, then it can update the policy and find and obtain the final task policy, which should be suitable to solving that specific problem. So here, if we have the end, let's say moving to the right, in the beginning, it has to just explore a little bit, moving left, forward, backward, and try to understand, okay, what is the actions, what is the behavior that would be, that would make my task more clear. And once I have those information, then I can use those information to update the policy in the right direction. So this is why we need an exploration policy other than a task policy. And the exploration policy should produce meaningful and informative actions or trajectories so that we can optimize our main policy or task policy as efficient as possible. Here, I'm also using some terminology that I would like to introduce them here. So whenever I'm talking about meta learning, I am typically meaning the update of the exploration policy. It's also being called outer loop optimization. Maybe it would have been good to actually show why it's called outer loop and inner loop. But anyway, the inner loop is whenever you're having one given task and you have some trajectories that are sampled, that are generated by the exploration policy, And whenever you're basically using those trajectories, or let's call them rollouts, to update your task policy, then we call it adaptation, because it adapts itself from the exploration to the task policy. It's also called inner loop optimization. Here's just an example of a trained meta learning policy at the meta test time. So the agent is, I guess, in here, and it has to go to basically to a position in this maze. Doesn't know where to go in the beginning. So at the very beginning, the agent basically uses the exploration policy to explore the maze a bit. And based on these trajectories, it can identify, okay, this is my task. And because this is the task that gives the highest reward. And then after that, it updates the exploration policy and obtain the task policy, which bring the agent from the third position to the goal position immediately. Is there any questions so far?
So with the exploration policy, is the goal of that one to collect as much information as or as useful information as possible, so that then it can use this data to solve the task?
Exactly. This is the basic idea with the exploration policy. And again, remember that here we are talking about few-shot learning. So again, very similar to this task that I talked about before. Here, for example, you only have 5 examples for the positive class and 5 examples for the negative class. That is why it's called few-shot problem setting. Here, we can't assume that the exploration policy have access to a lot of data, but it has to also just sample few rollouts, and based on those few information, based on those few rollouts, try to make them such that it can get maximum possible information from the data. So that is like the main objective for the exploration policy.
All right, thank you.
Maurice, thanks for asking. Okay. Now, I guess I have tried to briefly describe what is the setting and what the problem is. Now I'm going to go into some more details about what are possible solutions for this problem. One very straightforward solution to this problem is the one that can be given by the POMDP view, or partial observable MDP. Here, we're assuming that the task is the missing information from the state that is given to the agent from the state space. So, considering this, then we can use all those policy training algorithm that works with POMDP setting to first understand or extract information about the unobservable variable, which is here is the task. And then once this piece of information is available, you can assume that, okay, you have the full information about the problem, and you can apply a regular policy training algorithm to learn a solution for that. So maybe you may ask, okay, now we were supposed to learn something that would actually make our problem simpler or more data efficient, but we're doing it the opposite probably, because now we're assuming that we don't have access to the task information. And if we train this agent with lots of tasks, basically this would make the problem setting even harder, and it would be more difficult to learn a policy that can understand what the task is and then solve the task. So then the question may be, where are the benefits of meta learning? So the thing here is that, again, remember that we are interested about learning common structure between different tasks. And this is one way to obtain the common structure. So there are some papers calling meta reinforcement learning as fast reinforcement learning through slow reinforcement learning, and this is very correct. So in order to achieve a reinforcement learning algorithm that can learn faster, we have to actually have a much slower and more data inefficient policy training, or let's call it meta policy training. And once this phase is done, we should have learned the common structure between different tasks and model them by like this hidden variable, and using which we can now solve new tasks at the test time more efficient. So my main point here is that meta reinforcement learning is super slow, super data hungry, even worse than what we had before. But once it's been trained, then it should have learned the common structure between different tasks. Whenever a new task is introduced from the task distribution, it should be able to solve it much more efficient. Do we have any question here? Okay, let's move on. Okay, that is like one of the possible solution that correspond to this POMDP view. One paper that I want to talk about is, as I said, fast reinforcement learning via slow reinforcement learning. And the basic idea, as I said, is to basically consider the task as the hidden variable and use recurrent policy training algorithm in order to first understand the hidden variable, which is the task. And then once we clearly know what the task is, then we can basically train the policy or train the agent with full information. Yeah, do we have any question about this problems, this solution here?
Could you please elaborate what is episode 1, what is episode 2, and R2D2, R0D0?
Sure. H is the policy, and we provide the first state S0 to the agent. It performs the action A0, brings the agent to the state S1, gives reward R0, R0 and S1 given to the agent, and also D, I guess it's the done signal. So it says if the agent has to terminate or not. So for a step function, you typically assume that you have basically access to the next state, next reward, and the done signal, done or terminate. So that's like the information feeds back to the agent.
So this D2 is like means terminated. So you stop.
Yes.
So that's why there's another episode.
Yeah.
Thank you so much.
No worries. And then the hidden state of the agent is passed from one time step to the other and updated based on the information the agent has observed so far. Important thing is that the hidden state would be maintained only during one trial. And if you just start a new trial, you can assume that the task probably has been changed. So that's why you would initialize your hidden state again and continue training. So yeah, if you're interested, please have a look at this paper. It's a very nice one, talking about how we can train a recurrent policy for meta reinforcement learning. Another paper, which is also very nice, done by Kate Ruckley and the others, you can see the name here, is latent variable policy training, or let's call it efficient off-policy meta reinforcement learning via probabilistic context variables. I think this paper is called Pearl, if I'm not wrong. I don't know why, but I have to double check to be sure about that. But in this paper, they are basically they're not using a recurrent network, but they are trying to understand the task identity by using an encoder structure, which assign a distribution over latent variable z condition on the context. And the context here is basically the state, action, transition, and the rewards that you're receiving for the current task. So you would just give every tuple to an encoder. The encoder basically would assign a distribution over z condition on C1, which is this guy. And then you would aggregate all this information together, and you would learn a distribution over the z latent variable condition on all these guys here. And once you have learned the distribution over z, you can start sampling from that z. And these samples can be given to a Q function and a policy function, and then update the Q and policy by having access to this latent variable z here. Yeah, the main idea is that, okay, if you want to learn a Q function, the Q function would be different for different MDPs. And the basic idea here is that we represent each MDP with a latent variable, and then you can actually use regular, let's say, soft actor critic algorithm here to train both the Q function and the policy. Is it clear how this method works? I mean, of course, I'm not giving too much detail about this. I guess I have a question here. If the benefits of meta learners come when they have already been trained, are there standard meta learners already available out there? Example one based on ImageNet that we can play with, or is it not common yet? I think it's becoming more and more common these days to actually think about meta learning benchmarks, and also meta reinforcement learning, most modern meta reinforcement learning benchmarks. And I'm pretty sure you should also have access to the trained models for those benchmarks. You can, of course, then download them and play with them, test them. But if your question is about having like a meta model that would be like general enough that can be applied to many problem domain, I'm not really sure about that, but there are definitely, for ImageNet, definitely there are a lot of them. So you have to just read more about, I mean, just try to find some papers that are basically develop their algorithm on, let's say, ImageNet, and they must have also provided their code and trained models. So from this aspect, you should have access to the models and benchmarks and also data. Is this an answer to your question? I think we're not there yet to have something general. For NLP task, I guess there are some more general models. And I've seen people playing with NLP models, but for images, I'm not really sure. I think the most general thing you can find is those networks that are just trained on ImageNet, for example. Yes, natural language processing, NLP, right. Okay, do we have any question about this problem formulation or versus solution? Good. And by the way, there is also a YouTube talk done by Kate Reckley, and she's talking also about meta reinforcement learning. So I really encourage you to also look at that lecture. So it is a very nice lecture, I would say. Okay, let's now talk about optimization-based method reinforcement learning. So what I talked about mostly is known as black box meta learners, but now I'm going to talk about more optimization-based meta learning that are based on gradient descent rule. Remember that I talked about a fine-tuning procedure in which you would have like an initialization theta, which is pre-trained on another task. And then we have our trained data for the new task. Then we basically want to use gradient descent rule to optimize the theta parameter such that the final output would be more suitable for the task which is represented by this training data set. What we can do here, how we can improve this gradient descent optimization rule. One option is to find a better parameter initialization theta. That is one option here. So if we have our initialization somewhere closer to the optimal value, or but also by considering the loss landscape, maybe there's some optimal position in which you can put your initialization, and that initialization would be more suitable to adapt it to different downstream tasks. Of course, you can play with the learning rate and do some and optimize that. You can also work with loss function. So the loss function can be designed such that it would be easier for gradient descent to optimize the parameters to a good solution. There's also a lot of interesting work on this topic. For example, meta curvature is one of those papers that is very interesting considering this concept. And I really encourage you to look at that paper as well. And finally, we can also play with the training data and find better support examples that can be used to update the loss function, to update the parameters to a more appropriate one for our final task. So these are basically the options that we have with gradient descent optimization to optimize some pre-trained parameters to a good solution for the current task. Now I'm going to talk about MAML framework or model agnostic meta learning. So it's basically MAML is try to use fine-tuning, but it tried to obtain a good initialization for the fine-tuning based on gradient descent. So let me first start by describing this figure here. Here, the solid lines represent meta learning. Remember that I said that we have two different phases. One is meta learning or outer loop, in which we optimize the parameter theta. And we have also an inner loop or adaptation in which we're given a task, we are adapting the parameter theta to some parameters phi here. So MAML basically works like this. Maybe it's easier if I go and describe the loss function. Maybe you already can remember this loss function from my previous slide. You remember that we had like a meta learner, which was like, I denote them by F, but here, instead of F, we will have a gradient descent update for the meta learner. So basically, we're assuming, I guess, I don't know if it's, let me see if I can go back to that slide. Here. So we were assuming that the parameter phi are given by a function f. Here it's again the same assumption. So the parameters phi, basically the result of this update rule would be the parameter phi for a given task. But the function is actually a gradient descent rule in which we are given basically a support training example, and initialization, which is found by theta. We run one gradient descent step rule on the initialization, and then we obtain the parameters, the task-specific parameters. And we are, here we have min, and here we are basically minimizing the loss, which is computed on the query examples. And our goal is basically to optimize the theta parameter, the meta training parameter, such that we can find a good initialization theta that after one gradient descent can solve the task. So if you look at this figure here, let's assume that this is our theta, the initialization that we found by meta training. So if it wants to adapt to different tasks, like this, like task 1, task 2, and task 3, we should be able to use one gradient descent update with the learning rate alpha, such that from the initialization, we can move on to different possible solutions. So this is basically the main idea behind MAML framework. Do we have any question here?
So is this a realization of the F of theta, or what was it before?
This is
Like,
one way to implement.
yes, exactly. Whereas F, the one you showed first, is more that's how we would want it to be, and this is one implementation of it.
Yes, this is an implementation based on gradient descent.
Yes.
You can also train another neural network. I'm going to basically talk also about that. In some part of my research, I train another neural network that would generate a different neural network, so that, the parameters, if we call them phi is not coming from gradient descent, but it comes from another neural network. Yes, please, we have another question.
And just checking, this is in general, right? This has nothing to do with reinforcement learning for now. Like,
it's a general formulation that then
okay.
This can be applied also to reinforcement learning. I'm going to talk about it in the next slide.
Thank you.
Great, thanks for the question. Okay, do we have any more questions for this slide? The parameters theta is just initialized randomly, like any other neural network. And then this initialization, the theta itself is an initialization for gradient descent, but the theta itself is initialized randomly and then updated based on this loss function, such that you can basically find a good initialization for gradient descent update. Is this the answer to a question?
But if the theta is initialized randomly, then why this meta learning is better than regular reinforcement learning, because you are starting from the scratch again?
No, it's basically there is something that you have to take into account. As I said, we have a slow process, which is meta learning, and we have a fast process, which is the adaptation part. So in the meta learning, so we typically have no other option than just initializing from a random solution. Otherwise, it would be called meta learning. So if you have meta learning, then okay, that initialization can come from something else. But in meta learning, we typically assume that we start randomly, but we have a very slow process, because in that process we're optimizing over not only one task, but over a batch of tasks that are sampled from a distribution of tasks. So, and then we, at the end, whenever this slow process is converged, we should have found a good initialization. It's not initialization anymore. It's a theta parameter. We have found a good parameter for our meta learner. And indeed, our meta learner parameter is an initialization for gradient descent. But yeah, you should not confuse these two things with each other. Is it clear now?
So if I understand it correctly, so the adaptation part is the reason that it gets better than regular reinforcement learning. Basically, if we do only look at this meta learning by itself is slower than doing it just random directions as we did before.
Yeah, this is true. So if you only have one task and you only care about that particular task,
Yeah,
for sure you
exactly.
should not do meta learning, because
Yeah.
meta learning is very basically data hungry. But if you want to actually learn this learn task that would basically do better next time on another task, then one option is to learn common structure that exists between tasks, like very similar to what human does. So for human also, we try to always learn the structures between the common structure between different tasks, and use those structure to actually improve our skills. So whenever you're given a new task, let's say you want to learn table tennis, but previously you have some experience of actual tennis, then you can, of course, use the information that you already acquired from playing tennis and reuse those knowledge, those skills, whenever you're basically want to learn table tennis. So we human always do this. For agents, if you don't care about learning the common structure or being better at next time at learning a new task, then you should not really do meta learning. But on the other hand, if your goal is to learn something and then do that over and over, and you would like to be better and better next time, especially for robotic, it's very important. So let's say if I want to do, for example, if I want to learn a pouring task, I don't want to start from very, very scratch.
Yeah.
I would like to actually reuse some of the skills that I've learned before,
Exactly.
like grasping, pick it up, and probably, whatever I can learn from other tasks, from for the perception side, for the control part. I always want to reuse those information to be better next time I'm solving a new task.
Last question is the adaptation in MAML, in MAML, the adaptation or inner loop is the same. How is that work? Because you explained the meta learning part. What about the adaptation part?
A very good question. Remember that I said that we have a function, meta learner, f theta, that is like given our support example.
Yeah.
And
what
the
about
output
the
of
theta? Yeah.
Yeah,
I'm asking about the G theta. Yeah.
Yeah. The output of f is the parameters phi that are our adapted parameters. So here, the adapted parameters, assuming that we have theta as the meta learner parameter, the adapted parameter are the one given by this gradient descent rule.
So that's the G of phi.
G itself is can be a classifier. This is like phi. I mean, the parameters of the classifier.
Okay. Thanks.
Okay, good. Now let me go and provide a little bit more information about reinforcement learning with MAML. One thing that I have to mention here, MAML works the best when you're using policy gradient algorithm. And just to remind you about policy gradient, first, our objective is we want to just maximize the expected value of R tau. I mean, I just missed an R here. Our goal in reinforcement learning is to maximize the expected return over the trajectories which are sampled from the policy. And so for policy gradient algorithm, we can find the gradient of the objective with respect to the policy parameters using this. This is like, I guess you should have already learned how policy gradient works in the first two lectures. Where you're going to use policy gradient rule both for the inner loop update and also the outer loop update. This is a computational graph. Whenever you're doing the meta learning with MAML. So if you're assuming that we have a meta policy, pi theta, these pi theta will be used to generate some sequence of some, let's say, rollouts, and for one specific task. I mean, we're also assuming that we have a given task, we have a meta policy, then we generate some rollouts, and then apply the gradient descent rule based on policy gradient to obtain the adapted policy. Here is the inner loop update. And then we use the adapted policy, and given the same task as being used for the adaptation process, we generate some new trajectories, and then we compute the return here. And in order to optimize the parameters of the meta policy, I mean, now I'm talking about meta learning part. I mean, previous slide, I was talking most about meta test phase, but now I'm talking about the meta train phase. So in the meta train phase, we first update the meta policy to obtain the adapted policy. And then once we have the adapted policy, we use that to generate some rollouts and compute the return. And now our goal is to actually optimize the parameters of the meta policy, which is our outer loop optimization. And we do it by basically, this is like the credit assignment that you have to do. First, assign the credit to the adapted policy and then back to the meta policy. And for this, you would need to compute the Hessian second derivatives of the objective with respect to the parameters of theta. I'm not going to go into more details, but if you're really interested about finding out how these parameters are computed, I really recommend you to look into this paper. It's very good. It actually have very nice derivation of how the gradient of the objective with respect to the meta policy can be computed. Do we have any question so far? All right. Then I would like to first point out to some of the problem that we have with this solution. The main problem, the biggest problem that we have here is the fact that when you're using policy gradient, you're always assuming that you have access to very informative reward, and which is quite dense and is given like at every time step. Otherwise, policy gradient does not have a chance of learning a policy in sparse reward learning settings. So in order to avoid this problem, people has tried to change MAML framework to other setting. I mean, I already talked about the Perl framework, how it uses SAC algorithm, for example, to deal with to better deal with sparse reward setting. But what I will gonna talk about in my next slide is how we can use generative models in order to deal with the sparse reward part and still being able to apply MAML framework to obtain a policy using generative models. So remember that this is our general policy optimization framework or formulation. As I said, we are basically assume that the full trajectories are generated by a generative model, and we only gonna train a sub policy, which is a contextual multi-unbanded problem. It's not a sequential decision-making problem anymore. And the good thing about here is that we don't have the problem with the sparse reward anymore, because whatever action you are choosing, you would have a reward in the end, which is quite informative. And this makes it possible to apply MAML to basically learn both the sub-policy or the generative model. First, I'm going to talk about how the sub-policy can be trained using MAML by assuming that the generative model is fixed. Okay, we have already, it's already 3:30. So I assume that some of you would like to end here. So what I can suggest is that if you can give me 3 minutes, I will go through the remaining slides very fast. And then I can overstay until 4 for if you have any question, and those of you that needs to leave earlier, you can actually do that. If it's fine, then I would go for the rest of the slides pretty fast. Or is there any objection? Good, then let's do that. Here I'm going to talk about one of the application of meta-learning for sim to real transfer learning. Assume that you have you can learn a policy in simulation, but you would like to actually transfer the learned policy to the real world, as I described earlier. This is a hard problem. Typically, if you do that naively, it doesn't work. One way is to actually learn a robust policy in simulator and hope that the robust policy would still work, because the parameters of the real world, the dynamics of the real world should be still similar to the dynamics in the simulation. But another approach would be to also learn a learning agent in simulation using meta-learning, and and then transfer the learned agent from simulation to the real world, and hope that this learning agent would generalize better to the unseen condition in the real world setting. Then basically we can define a meta-learning setting here. We can actually, in simulation, try to do something we call it domain randomization, try to randomize many different parameters of the setting so that we can create different dynamics and therefore different MDPs. So this is like this table shows how we have randomly changed different parameters for this task setting. And then we train a meta-learner that is able to learn, to adapt to these different MDPs, which are randomly sampled in the simulation. Once we have this meta-learner for the real world setting, we're basically use the meta-learner and try to collect some rollouts, use that rollouts to update the meta-learning and obtain the final policy for the task. Here we're using MAML again for this. So just showing you one video. This is now before adaptation. So as you see, this is the exploration policy. It tries to basically hit it, I guess, as hard as it can to understand what are the parameters for the task. And now this is after adaptation. Okay. Now my next slide is about how you can basically use meta-learning for multi-robot policy training. So as I said, we can learn different things on different robots, but how we can transfer the knowledge that's been learned by one robot to another one. So I'm very quickly gonna go through this. Here, we can assume that our D policy, again, consists of task-specific and robot-specific. This robot-specific part is the generative model, which can generate different action. And then we can assume that we have access to a large number of different robots. And then we use meta-learning here, again, MAML, to learn initialization over the parameters of the generative model. And whenever we introduce a new robot, these parameters can be adapted to the generative model, which is suitable for the new task, provided only a few demonstrations. That's our research. What we did, we had 400 different robots in simulation, and then basically trained a generative model using MAML. And then at meta test time, we showed that we can basically adapt the parameters of this policy to the good generative model for this robotic platform in a few shot setting. Okay, I have to skip this. Only thing I want to say about this framework, the nice thing about it is that given a support set, it first maps it into the latent space. And the latent space basically try to capture the similarity between different tasks. And then from this latent space, we use a generative model to generate parameters for neural network. I mean, we generate a generative model, better to say here, and then use MAML to optimize the parameters of that generative model. And as I said, the nice thing about this formulation is that we learn a latent space in which different tasks that are similar to each other can be mapped together. So, for example, for the Yumi robot here, all the purple dots shows the 100 different Yumi robot that we have. An interesting thing is that they all put together, which means that the encoder that we have here has potentially understood the relationship between different robots. And here each point shows a completely different robot. So it's basically built on top of Yumi, but the robot itself is different. So for example, it would have a different length for this joint of the robot. And these are some results. Let's skip them. Then now I can say I am done with my lecture today. Thank you all for participating in this lecture. If you're interested about learning more about meta learning and meta reinforcement learning, I recommend you to look at the course which is given by Professor Chelsea Finn at Stanford. And the course is publicly available, all the lecture materials and also the videos. And again, I found the lecture given by Kate Reckley is pretty interesting on multitask and meta learning. I guess it's more about reinforcement learning. Probably I'm missing something here. I put also the YouTube link to Kate's lecture. That lecture is also a part of that course. So yeah, this is it. I would be happy to answer your question if you have any. Does meta-learning make interpretability better or worse? Since any issues with meta-learner will apply to many agents and problems, they may have issues in common, but we could also then fix these issues in one place. Does that also mean, however, that we need to understand the meta-learner to fully understand the individual adapted agents? No worries. One thing that I can say here is that potentially meta-learning can result in more consistent solution. So especially if you train this MAML and you try to obtain one initialization and then use that initialization to adapt to different tasks, one can say that you would adapt to different tasks more consistently, but is it like more interpretable? I'm not really sure. Unfortunately, this is not my research, but I'm pretty sure there must be some papers about interpretability when it comes to meta-learning. No, unfortunately, I don't have a very good answer. Maybe someone else from the audience can answer this question. All right, sorry for that. Thank you.
A question about maybe this is specific to what meta-learning algorithm you use, but when you're doing the adaptation when you're doing the inner loop, are you training the meta-learner at that point, or are you just training the I don't know, learner?
Yeah, the task-specific model, let's call it. Yeah, that's a good question. In inner loop, we only adapt the meta-learner to the task-specific model. We don't do update the meta learner. The meta learner itself is only trained in the outer loop.
Yes. So when you have those 5 different robot policies, you can't then combine them back into another meta model. Then
Basically, let's look
yeah,
at here.
right. There's
so
a divergence point.
Yeah, you're using the information from these tasks to move the meta learner itself, to the next point on this solid line. So this is the outer loop. We're updating the meta learner itself. But at the adaptation step, you're just adapting the obtained meta learner to this different task. But whenever you're doing in the outer loop, that was the inner loop. In the outer loop, you're aggregating the information that you get from each adaptation, like here, and try to update the meta learner itself. Hope this is more clear now.
So what you said there at the end confused me. So at some point you say that you're not teaching the meta learner anymore, like you're freezing the meta learner.
Basically, no. We have again 2 phases: one meta learning and meta training phase and meta test phase. At meta test phase, our meta learner is freezed, but during meta training, no, we're basically training the meta model, let's call it. And then in meta learning, there are 2 phases. One is the inner loop and the other is outer loop.
Yes.
Inner loop, you're assuming that your meta model is fixed, and then you adapt it to different tasks. That's like the inner loop. In the outer loop, you compute the gradient of each of the obtained solution. Let me go back a bit. No. Here. In the outer loop, in the inner loop, so inner loop is actually from here to here. That's the inner loop. So you have the meta model and you obtain the adapted policy based on the meta policy. So that's the inner loop. In the outer loop, you're trying to first you sample more rollouts from the adapted policy to compute return. In the outer loop, you're trying to basically find the gradients of the objective, which is constructed based on return with respect to the meta policy parameter, to update the meta policy parameter. And this is done basically by through something like this. So first you find the gradient with respect to adapted policy, and then from here to the meta policy. So this is the outer loop. In the outer loop, the goal is to update the parameter theta. But the inner loop basically is to adapt whatever we have here to a task which is given here.
But yeah, I think I understand that there's a flow of information back from the inner loop into the outer loop.
Exactly, and that's why we need to compute the second derivative.
Yes.
Because once for the first derivative is when you're updating the meta policy to the adapted policy. That's the first gradient that's computed. And then whenever you compute the output, you want to compute the derivative of the objective with respect to the parameters. And that's why you would need to find the second derivative to backpropagate the flow of, as you said, information to the parameters of the original meta policy, because that is what we want to update in our meta learning phase. One can say that at the meta learning phase, we don't care about the adapted policy. We only care about the meta policy. That is the product of meta learning. But whenever the meta learning is done, at meta test phase, we no longer care about the meta policy. We want to update it and obtain task-specific pulses, that would be the product of the test time. One interesting example is that if you train a meta policy to move forward and backward, so the meta policy itself does not move anywhere. It's just like trying to move, but doesn't move forward or backward. But it is a good initialization that after one gradient step, you would basically move in either direction. I have to correct myself because in practice, the meta policy actually moves a little bit because otherwise it can't explore. It has to move a little bit forward. If the tasks are just moving forward and backward, it has to move forward a little bit or backward a little bit to be able to understand how the reward look like. But as soon as, but that's just the level of motion that will be realized by the meta policy.
I
And
imagine that the robot arm would maybe flex the arm once or something just to get the actuation power or something.
right, but it has to, get something that would
Yes.
help it to understand what the task is. Because here in meta learning, we also have the exploration problem, which has to be done in order to understand the task itself. Did I answer your question?
Yes, thank you.
Great. We have also another question. What do you suggest for cases when performance evaluation for a specific skill can be robot dependent? Thank you. For example, some limitation for certain robots, some robots allow better precision, etc. That's a good question, actually. I'm not but very sure how the performance can be robot dependent, because if we have a task, then we can say that our goal is we can evaluate the robot performance based on the task. But let me think. For example, some limitation for certain robots, some robots allow better precision, etc. If you have some limitation, where do we need to learn those limitations then? I mean, that's very general, because definitely you can apply different solution. And for example, if you use generative models for that problem, then you may somehow solve those limitations by training a proper generative model. But on the other hand, you may not be able to learn a generative model to solve your problem. That's another problem. So that's why I'm saying it's a little bit too general to be able to give a concrete answer for that.
Okay, sure. No.
Do we have any other question?